Hello everyone, my name is Sharafzia and I along with my colleague Nuriya Chima and with the help of our professors Dr. Ashraf Iqbal and Professor Yasser Hashmi here at Lahore University of Management Sciences, we have conducted this research on problems in calculus faced by undergraduates, and I'll take you through it. In order to begin our study, we did a pilot study to ascertain whether students could convert data between graphical, numerical, verbal, and analytical interpretations. And the study was conducted on 5 people, and we found that students could not do this, and they had a substantial lack of ability in this matter. After that, I'm basically just taking you quickly through this before I introduce the main study that we did. In terms of a literature review, what we did was that we studied different theories of learning as to why there were problems in learning calculus, and we found out that there were 2 main problems. One was that students tried to apply rules. They tried to apply scripts. That is that they were looking for ways to apply set rules that they had learned earlier, so they could just apply that and get the answers. And apart from that, students stored their concepts as discrete students stored interlinked concepts as discrete units in their memory, with no connections or little connections between them. For example, they would store differentiation and integration as two discrete concepts without a link, such as the integration is the reverse of differentiation and vice versa. So these types of links would be absent between concepts, and students would make these concepts into distinct units, and they would keep on doing so until the discrete amount of concepts would get so large that they would face a problem, and there would be a failure in learning, and students would fail in their subjects and suffer in learning the concepts required. We also studied tutorial studies, in that we went to attend tutorial classes handed out to advanced calculus students. We couldn't have basic calculus students in this year because not this year, in this semester, because in this semester what happened was that the course being offered was advanced calculus, and calculus 1 had been offered the semester before, so we only had advanced calculus students to work with, and we saw the tutorials that were handed out to them. And once again we found that in these tutorials there was a great emphasis on abstract learning as opposed to real world learning. So when we first presented our findings in our class, we received the following feedback questions, and I'll address them quickly. What were problems in learning calculus? So that basically has been explained in that storing concepts as distinct units, and trying to apply formulas when it could be a question about anything. So the second question was, why was Harvard calculus introduced? And because we have a deep interest in Harvard calculus approach, in that it emphasizes real world learning, what we think as to why Harvard calculus was introduced was that Harvard calculus tried to go about things in a way that it taught students to learn real world concepts first and then build their abstract concepts on that. So this was why we felt that Harvard calculus was introduced, as opposed to the purely abstract form and analytical form of concept building that is currently in the pedagogy right now. So then we did a quantitative analysis of the difference in different texts. In this we consulted 3 main texts. One was the A-level text by Bostock and Chandler. Then there was the Fellow of Sciences text that is being taught at that is the most taught textbook in Pakistan, and that is the official textbook as authorized by the government of Pakistan. And then there is and then we converted these 2 books with the Harvard calculus approach to find out as to what was the difference between analytical, verbal, graphical, and numerical examples in all of them, and how many real world examples were there, how notational was their approach, how abstract was their approach, how concrete was their approach. So we consider those questions. What is happening in FSCA levels and undergraduate level? So the same thing, we found out that there is an emphasis on script based learning, and students are taught basically to look for a formula, so we can't really blame them if they try to find a formula in every single case. The regularities involved, regularity is basically a psychological term for the properties that make up a concept. So the properties of basic differentiation and integration, you can say, are functions, limits, continuity, recognizing differentiation as rates of change of one variable with respect to another, and recognizing integration as its opposite and as area under the curve. So these, you can say, are basic regularities involved. So after that, after what I have explained, we did a comprehensive study in that we handed out 2 questionnaires to students. One was based on concrete concepts that tested continuity, limits, basic differentiation and integration, and one was an abstract questionnaire that tested the same thing. The study was conducted on 15 students, 12 of whom were currently studying advanced calculus, and 3 who had already done calculus 1 before. So we had 12 freshmen and 3 juniors, and this study was conducted in 3 modules, 2 of which I have already explained, the abstract and the concrete ones. And the third module was related to problem generation, in that we asked students to generate problems so that we could gauge as to what was their understanding of concepts. So I'll take you to the questionnaires. Module A had 4 questions. The first question was, a car accelerates from rest to a top speed of 100 kilometers per hour and then decelerates back to rest. Is the differential of this car's distance time equation positive, negative, or a mixture of both? Explain briefly. And if the deceleration begins after 10 seconds, what do the first 10 seconds represent in terms of limits? Okay, so this was a question on basic differentiation, and we had 10 correct answers for part A, in which they had to tell what was whether the differential was positive or negative or a mixture, and we had 2 correct answers for what were the limits representing, and 9 out of 10 of the first part that was answered correctly involved it involves a correct explanation. B part had 2 correct answers and 2 correct explanations to go with them. Then we had a question that there was this formula car that goes around, that makes 3 loops of its circuit, and then if it crosses the finishing line, what is the velocity? 4 students managed to answer that question, with only one of them offering an explanation as to why. The answer was 0. And then there was the third question: a dancer travels steadily from rest to a top speed of 12 steps per second, and then decelerates back to rest another 4 seconds. Okay, so this question had correct answers. And then the final question was about a frog that jumps 2 centimeters in 2 seconds and then rests before jumping with the same velocity again. So there was only one correct answer with the correct explanation. After that, we go to the abstract questionnaire, in which is to draw a rectangle in a Cartesian coordinate system, in which the upper left corner was represented by the second question was, what does the integral of a velocity time equation represent? The third question was that Superman is going back 6 seconds in time at a steady speed of 100 meters per second. Is his differential positive or negative? And the fourth question was, there's an equation that is discontinuous there's a line that is discontinuous at the point x equals to 5. So can a differential be applied on this line, and if not, what changes could be done so that the differential can be applied? So for question number 2, we had 2 correct answers for question 1. Question number 2 had 9 correct answers. Question number 3 had 3 correct answers, and question number 4 had 8 correct answers for part A, 6 for part B, and all 8 and all 6 of them were provided with explanations. And for problem generation, we found the same thing, that students focused on they only gave us analytical questions, which again reinforced the idea that students were being taught in an analytically intensive way, and we think that that should be changed, and that is our conclusion, in that we state that students that we basically are proposing that Harvard Calculus should be given a chance, and that students should be taught, their concepts in a way that they are brought up first by being taught real world examples, and then they are taught abstract concepts, so that they have a better understanding. That I believe would be a better way of teaching calculus, because otherwise, if you give students questions that are not based on strictly analytical questions, you get poor results, as shown by our study. And that's all I have to say. Thank you very much, and do comment.